Hi, and welcome to the first presentation for Week 2 in IS 286. In this presentation, we're going to talk about the role that spanning tree plays in modern networks. Most of you are probably familiar with the concept of redundancy and how important it is for network performance. But you may not realize that without spanning tree, redundancy within the LAN would be virtually impossible. Take a few seconds to check out the topology demonstrated on this slide. Now, first of all, we can see that the S1 and S2 switches are access layer switches. We know this because both switches have end devices connected to them. Depending on the size of the network, the S3 switch may be another access layer switch, or it may be a distribution layer switch. Okay, so we pretty much know how our switches fit into the overall hierarchical network design. So what else do we know? Well, based on the connections and the types of connections, we can see that we have some redundancy in place. If you look closely, you can see that each switch has two different ways to send a packet to any of the other switches. For demonstration purposes, let's say that PC2 is needing to send some packets to PC4. Well, the most direct route is through S2's F01 port connection. But what if that connection were to go down? The S2 switch can still get the packets to PC4, but instead of initially going through the S1 switch, they will have to go through the S3 switch. We could go through several similar scenarios here that would highlight the redundancy that is in place, but I'm sure that you get the point. Redundancy is necessary for keeping a network operational. This is true at both Layer 2 and Layer 3, but our primary focus for this week is Layer 2. Redundancy at Layer 2 introduces a problem that we must deal with. The problem that we must deal with as a result of having redundancy at Layer 2 is a Layer 2 loop. Using the topology that we looked at on the previous slide, I'll explain how the loop occurs. First, PC1 sends a broadcast frame to switch S2. When S2 receives the broadcast frame, it records PC1's MAC address as being connected to port F011. Then, S2 forwards the broadcast out all ports except for the port on which it was received. When the broadcast frame is received by S3, it records that PC1 is available via its F02 port. When S1 receives the broadcast frame, it records that PC1 is available via its F01 port. Now, S3 and S1 forward the broadcast packets out every port except for the port on which it was received, which means that S3 sends the frame to S1 and S1 sends the frame to S3. At this point, when S3 receives the broadcast frame from S1, it incorrectly records that PC1 can be reached via the port on which it received the broadcast, which of course is not correct. The same problem occurs when S1 receives the broadcast frame from S3. Now, both S3 and S1 forward the broadcast frames that they received from each other out all ports except for the port on which each broadcast frame was received. This means that both broadcast frames are now headed for switch S2. When S2 receives the broadcasts from S3 and S1, it updates its MAC address table with incorrect information and then forwards the broadcast out all ports except for the port that each was received on. This means that the broadcast from S3 is sent to PC1, PC2, and PC3, but not only that, it is sent to the S1 switch. The broadcast from S1 is sent to PC1, PC2, PC3, and then the S3 switch. You should be able to see at this point that this cycle will continue on and on. Keep in mind that when a host is caught up in a switching loop like this, the host is unreachable. Now, with the loop scenario that we just went through in mind, imagine if all the hosts connected to S2 sent out broadcast frames. At this point, it would not take much time and we would have broadcast frames all over the place. Hosts send out broadcast frames all the time, so this scenario would occur if layer 2 loops are not prevented. This type of scenario is referred to as a broadcast storm. A broadcast storm would bring a network to a screeching halt. So what do we do about layer 2 loops? Do we just not provide redundancy between our switches? Well, in many cases, network downtime is something that is not acceptable. If we have no redundant connections, the network will be down for the amount of time it takes to diagnose the problem and swap out the cable. If the cable is 80 meters long and runs between the floors of a building, what do we do then? The network could be down for a long time. But what about a smaller network? Could we truly and totally avoid layer 2 loops simply by not providing redundancy at layer 2? Well, the problem is that the loops can still occur. Wiring closets are often tight spaces and cables are running everywhere. Many of the cables are running into and out of conduit, and determining where all those cables go can be extremely difficult. What if someone accidentally duplicated a connection? Another possibility would be an employee bringing in their own hub or switch and connecting it to the network by using the connection in their office or cube. They could, without realizing what they are doing, create a loop themselves. And even in a smaller network, would we really be okay with not providing redundancy? Sound network design principles should be followed no matter the size of the network. Unusual designs or workarounds may not seem like a big deal in a smaller network, but what happens as the network grows? If the foundation is bad, then the network will not be what we need. The bottom line here is that layer 2 loops are unavoidable. So how do we stop them from disabling our network? Well, since we started out this discussion mentioning spanning tree, you probably already know that I'm going to tell you that the spanning tree protocol is the answer. What spanning tree does is it eliminates redundant paths by blocking them. The actual physical path, in other words the redundant link, is still there, but the switch port is put into a blocking state, thereby eliminating the logical connection. If something happens to the connection that is being used and it goes down, then the blocked port can immediately and automatically be unblocked so that the connection between devices does not go down. What happens is STP recalculates the path using the spanning tree algorithm and then unblocks the necessary switch ports. So let's look at how this works. Using the example topology that we used before to demonstrate how a layer 2 loop occurs, let's look at the result of STP. First, you'll notice that the connection between the S2 switch and the S3 switch is blocked. What is happening here is that spanning tree is blocking the redundant connection by blocking port F02 on S3. This way, S2 only forwards the broadcast along one connection to S1. The broadcast will reach S3 via S1. Since the connection between S2 and S3 is blocked, that's where it ends. No loop can occur. We just talked about the results of STP, but how exactly does it work? How does it decide which ports to block? Well, the spanning tree algorithm is what STP uses for this. The spanning tree algorithm, or STA, designates one switch as being the root bridge. We'll talk about how the root bridge is elected in a little bit, but for now, just realize that the root bridge is used by the spanning tree algorithm as the reference point for all path determinations and port assignments. Once STA has determined the paths that will be left open, it configures specific ports for one of three distinct roles: root port, designated port, or non-designated port. Let's talk about these three port types for a minute, and we'll come back to the topology with port designations on this slide. Root ports are switch ports that are the closest to the root bridge. The connections to these ports will always be open. In other words, root ports are not blocked. Designated ports are ports that are not root ports, but are still not blocked. Non-designated ports are ports that are blocked in order to prevent loops. Okay, so now that we know what each of these three port types are, let's go back to the topology that we were looking at. Notice that switch S1 has been designated the root bridge. Since F01 on S3 and F01 on S2 are the closest ports to the root bridge, these two ports are configured by STP to be root ports. Again, these ports will never be blocked. Also, notice that the ports on S1 that the two root ports are connected to are configured as designated ports. Finally, notice that F02 on S3 is configured as a non-designated port and is therefore in a blocking state. Understand that the role that a port plays in STP is determined by its location in relation to the root bridge. The root bridge will never have any of its ports blocked because they will always be connected to ports on other switches that are designated as root ports. Therefore, in the example that we are looking at on this slide, The only ports that could have possibly been blocked are F02 on S3 and F02 on S2. So why was F02 on S3 blocked instead of F02 on S2? We'll answer this question next in our discussion on how the root bridge is elected. After a switch boots, it sends out Bridge Protocol Data Units, or BPDUs, containing the switch's bridge ID and its root ID. The BPDU frames are sent out every 2 seconds. The bridge ID consists of 3 parts: a priority value, an extended system ID, and the MAC address of the switch. Also, by default, the bridge ID and the root ID are the same immediately after the switch boots, and therefore each switch believes that it is the root bridge. When BPDU frames are exchanged, each switch will compare its bridge ID to that of the other switches. If the other switch's bridge ID is lower, then that switch is designated as the root bridge. Once all switches have received BPDU frames from all other switches, then the final root bridge has been determined. Since this process takes several seconds to occur, the more switches there are, the longer it takes, all switch ports are blocked for the first 20 seconds that they are up. Now keep in mind that by default, the priority value of all Cisco Catalyst switches is 32768. Therefore, by default, the only difference in the bridge ID of one switch and that of another switch is the MAC address. This means that, by default, the root bridge is determined to be the one with the lowest MAC address. This somewhat random designation of a root bridge is not what we want to allow to happen, because the location of the root bridge is key to the efficient operation of a network. Fortunately, the priority value is something that we can adjust. There are actually 2 different ways that we can adjust the priority value, thereby designating which switch will be the root bridge ourselves. The first is to use the spanning-tree VLAN ID root primary command. This command will result in the priority value of the switch being set to a predefined value of 24576. Since this value is less than the default of 32768, the result is that the switch becomes the root bridge. Notice on the slide we are configuring the root bridge for VLAN 1. The other way that you can make a specific switch the root bridge is to configure the priority value to be whatever number you want, in increments of 4096, between 0 and 65,536. Using this method, all that you have to do is set the priority value to something less than the default value of 32768, and the switch will then become the root bridge. The second command line that you see here on this slide shows the command required to change the priority value. There is one other factor to consider when configuring STP for specific root bridge elections, and that is backup. What happens if the root bridge goes down? Well, we would be back to where we were in the beginning, which means that our new root bridge would be determined by MAC addresses. Therefore, we need to configure a backup root bridge. We can do this in one of two ways. The first is using the spanning-tree VLAN ID root secondary command. The second way is to configure the backup root bridge with a priority value that is lower than the default value, but higher than the priority value of the primary root bridge. I'm going to end this presentation by talking a little bit about current STP implementations. If you intend on taking the CCNA exam, you need to be aware of these and at least have a basic idea of what they are. Oftentimes, CCNA exam questions will only give you the acronyms, so you need to know what they stand for. First, there are 3 implementations of STP that are Cisco proprietary. These are per VLAN spanning tree, or PVST, and per VLAN spanning tree plus, or PVST plus, and then rapid PVST plus. PVST maintains a separate instance of spanning tree for each VLAN, as does PVST plus. Rapid PVST plus provides faster spanning tree convergence. Finally, there are 2 IEEE standards, and they are Rapid Spanning Tree Protocol, RSTP, and Multiple Spanning Tree Protocol, or MSTP. And this concludes the first presentation for Week 2 in IS 286.